Hi, I'm Adam and welcome to the second video in this Duino-Coin series. In today's video, I'm going to be walking you through, step by step, how to enter the schematic for this USB miner into KiCAD. Let's get started. This video is sponsored by PCBWay.com. The USB miners featured in this video series are made using PCBs manufactured by PCBWay.com. To order quality PCBs at a great price, head on over to PCBWay.com and upload your Gerber file for an instant quote. Duinocoin can be mined using an Arduino Uno. Note that the Arduino must be connected to a computer using USB in order to mine. The Arduino Nano is also capable of mining Duinocoin and is a lot smaller. But where would the fun be in using an off-the-shelf device when I could design and build my own? I want my miner to be in a similar format to a USB thumb drive, so it should have a Type A USB connector that can be directly inserted into my Raspberry Pi. And since I will not be connecting anything to the I/O pins, I can drop these from the design. This is the schematic for an Arduino Nano and is available for download directly from the Arduino website. Here we have the Atmega microcontroller, and those two pins 30 and 31 are the serial connection between the microcontroller and USB to serial UART. Now, if we take a look on here, you'll see that the TX pin connects to this TX wire up here, which is actually the RX pin of the IC. And here, the TX pin connects to the RX pin down here. So the TX and RX connections cross over. Here is the USB plug, and from pin 5, which is the plus voltage, we have a fuse going to the label VUSB, which is down here on the 5V auto select. Then over here is a voltage regulator for any power that's applied to pin 1 of J2. Here is the ICSP header, which stands for In-Circuit Serial Programming, which can be used to program the bootloader into the microcontroller. And down here are some smoothing capacitors across the input voltage for the USB connector. I'm going to base my USB miner on the Arduino Nano, but do away with anything I don't need. So I can get rid of the connectors J1 and J2, I don't need a reset button, and I can get rid of the 5V regulator since I'll be powering my miner directly from the USB port. I'll drop 2 of the 3 LEDs as I'm only interested in visual feedback when mining, and this will also keep the cost of the components down. I'm going to use a different USB to serial UART IC. The one I'll use is the CH340G. This IC comes in a few different flavours. The G variant has an internal oscillator, so this will cut down on external components. I'll still add an external oscillator into the design that can be soldered in place in the event that you are unable to source the G variant of this IC. This is the circuit for my USB Duino-Coin miner. You can see that I've dropped some of the components and the 2 main connection headers. Okay, let's run through entering this into KiCAD. So go ahead and open KiCAD. Click on File and then New Project. I'm going to create a new folder to save this project in. And I'll call this project Duino-Coin Miner version 1.1 because I've already drawn a version 1.0. So let's save the project in here and give it the project name Duino-Coin Miner version 1.1. And then click Save. Here's our project that contains a blank schematic and blank PCB layout. So open the schematic. That's the one ending in KiCAD_SCH. And the first thing that we're going to do before adding any components is to fill out this area here with the details of what this schematic is for. To do this, click on the button up here. I'm going to select today's date. The revision is 1.1. The title is going to be USB Duino-Coin Miner. And the company is going to be iNimbleSloth.com. And then click OK. To zoom in and out, use the scroll wheel on your mouse. Now, anyone who sees this schematic knows what it's for. To move around the page, press and hold the scroll wheel on your mouse whilst moving the mouse. I like to save the schematic regularly when working on it, so I'll click the Save button now. Next, I'm going to sort out the snap grid, so View and then Grid Properties. The current grid is 0.13mm, which is far too small for my liking. I'm going to go with 0.25mm. Right, now I'm going to start adding the components. The first one I'll add is a USB-A connector. To add a component, you can either click on this button here or press the A key on your keyboard. So let's search for USB. And here is the one I want, a standard USB-A connector. So, with it selected, click OK. I'll drop this in here by left clicking where I want it. Don't worry too much about the exact position, as you can always move it later. Power is going to flow into my circuit from the USB connector, and this is going to go through a fuse. So press the A key on your keyboard to bring up the symbols, and I'm going to search for a poly fuse. To rotate, press the R key on your keyboard. So next, I'm going to add the USB to serial UART IC. This chip is a CH340G. Note that the G variant has a built-in oscillator. In case you can't get the G variant, I'll be adding an external oscillator into the schematic. If you have the G variant like me, then you just don't need to solder in the external oscillator to the PCB. This way, your design will be suitable for both variants of the chip. I'll place this here. Right, now let's add the resonator. Rotate it with the R key. Next, I'm going to add a capacitor, so simply search for C. We need more capacitors. You can either copy and paste this one with the Ctrl-C and then Ctrl-V commands, or you can press the A key on your keyboard and add another capacitor, as we just did. Let's start connecting these components up. To draw a wire, place the cursor over the leg of the component and then press the W key on your keyboard. Now draw the wire and left click to connect it. Connect the USB D+ pin to the UD+ pin on the UART chip and connect the USB D- pin to the UD- pin on the UART chip. Next, let's connect the resonator to the UART chip. Remember, if you have the G variant of this chip, then you can still draw this, but you just don't need to solder it into place. Pin 2 of the resonator and pin 1 of the UART chip get connected to ground, so let's connect them together like this. And over here, click this button to add the ground symbol, or press the P key on your keyboard. Search for GND and then add the symbol here, and using the W key on your keyboard, draw a wire connecting it like this. These two pins on the USB connector get connected together and then connected to ground, so copy and paste this ground symbol. Next, let's connect this capacitor. This side of the capacitor is going to connect to a part of the circuit I've not yet drawn. When I do draw it, it will connect to a part called reset. So I'll add a label to this wire and call it reset. Now connect this label to the capacitor. The label is electrically connected to any other label that shares the same name. So using labels like this is a way of keeping the circuit looking neat and tidy without having lots of long wires sprawling across the page. I'm going to match the references of the components in the drawing to the one that I showed you earlier. I suggest that you do the same, as it will be easier when coming to lay out the PCB if you are using the same reference numbers as me. There are 3 ways to set the reference number, either automatically, which I shan't be doing today, manually by double clicking the reference number and changing it here, or by selecting the component and then pressing the E key on your keyboard, which enables you to change all of the properties of the component. So C1 is going to be 100 nanofarads. This chip is going to be U1. This will be Y2. The fuse is going to be F1. And the USB connector is going to be J2. Let's move this over to the left a little bit. To move a component, select it with the left click and then press the M key on your keyboard. Now you can move it with your mouse and place it where you want. Select and delete the wire and redraw it so that the fuse connects to the USB connector pin 1. Now add another label, this time called VSUB, and connect it to the fuse. So we'll have power coming into the circuit from the USB connector, through the fuse, and then into anything that is connected to a VSUB label. Then connect these capacitors like this. Please note that I made a small error when recording this video, and I forgot to add a GND symbol to these capacitors. Here it is in my original drawing. It will save you time later on if you add the missing GND symbol now. So here we have the USB coming into the circuit. Here is the UART chip, and these are the serial TX and RX pins which will get connected to the Atmega microcontroller. We can now connect these using labels, so add two global labels and call them TX and RX and connect them to the chip like this. Next, add a VCC power symbol and connect to the VCC pin of the chip. Right, let's save. Before we move on to the next section of the circuit, we need to tell KiCAD that the pins that are not connected to anything are not supposed to be connected to anything. We need to do this for the electrical rules checker, otherwise it will throw a bunch of errors. So what we need to do is click this button over here and then add a cross to each pin that isn't connected to anything. Next, let's add the Atmega microcontroller. To add this chip, either click the Add symbol button or press the A key on your keyboard, and then search for AT-MEGA328-P. Here is the footprint for the chip, and we can see that it's the through-hole variation. There is also a surface mount version available, just choose the variant that you have. I'm going with the through-hole component for this video. Let's place this here. So what do we need around this chip? We'll need a capacitor, so A key to add the components, search C, add the capacitor, R to rotate, and W to add the wires. Let's move this text, select and M key. This is going to be U2. And this is going to be C2. Add a GND symbol and connect to C2. These pins get connected together and then to VCC. Over here, the first three pins are not being used, so add the little blue cross. Then we'll connect a label to this pin called MOSI. And we'll connect another label to the pin below called MISO. Pin 19 will be connected to an LED, and this LED will be used to show us that the device is mining. The LED requires a resistor, so let's add that first. R for resistor, and R to rotate. Then search for LED. Rotate it and connect it with the W key. Then connect the cathode side of the LED to a GND symbol. I've drawn the ground quite far down as I'll be connecting other components to this. Next, let's add a resonator, so A key, search for resonator, select it and then rotate with R. And this gets connected like this. With the resonator selected, press the E key and this will become Y1 and it is 16 MHz. The resistor is R3 and the value is 1K. The LED will become D1 and I'm going to add the colour to the label. I happen to have a bunch of blue LEDs to hand, but you can use any colour that you have. We need to label this wire SCK, as it will connect to the SCK on the ICSP header. So add a label called SCK and attach. Then add a blue cross to these pins so that KiCAD knows that we're not going to be using them. Add a resistor symbol, rotate it, and connect it to a VCC symbol. Then connect the other side to the active low reset pin on the microcontroller. This resistor will hold the pin high, which will keep our miner running. The resistor is R4 and is 1K. Add another 2 resistors by copying and pasting. Oh, before I forget, we need to label this wire reset. This is because it will connect to the ICSP header and also to the reset label over here. Let's move this text about a bit so it's easier to read. Notice how when I move the text, there is a blue line connecting the text to the component it belongs to. Connect PD0 and PD1 from the microcontroller to these resistors. These 2 resistors will connect the RX and TX pins of the UART chip. Let's name them R1 and R2. Now, let's add the labels TX and RX. It's super important to get these the correct way round. If not correct, the microcontroller will not be able to talk to the UART, and then in turn your computer. Then these pins aren't connected to anything. Then add a GND symbol and connect to the GND pin of the microcontroller. Let's take a quick look at my original circuit. So we've drawn this, and we need to add these capacitors next. These are smoothing capacitors that are directly across the power supply. So add 3 capacitors, these become C3, C4 and C5. C5 is 100 nanofarads, C4 and C3 are both 4.7 microfarads. Connect them like this. Add a GND symbol at the bottom and a VCC symbol at the top. So next, let's add the ICSP header and the 5-volt auto selector. Press the A key and search for con_02x03. And we need the odd even version, with the pins running from left to right 1, 2, 3, 4, 5, 6. Then connect this to the following labels and GND symbol. And this becomes J1. Then for the 5-volt auto select, we need to add a diode. Connect VCC to the cathode and V-sub to the anode. This is D2 and it is an SS1P3L. Next, I'll tidy it up a little by drawing some boxes around the various sections of the circuit to make it clear what each section is for. So, using this tool, draw around each section like this. Now, using the text tool, add some text to say what each box is for. Fantastic, looking great. Before we move on to assigning footprints to the components and then to laying out the PCB, we need to let KiCAD know which of the connections are power by adding a power label. These labels are used by the electrical rules checker. Within the power symbols, search for PWR_flag. By adding this here and connecting it to the VCC, KiCAD knows that this is considered the power. We need to do the same for a GND connection. We don't need to add a power flag to each VCC or GND, as remember that KiCAD already knows that each VCC is electrically connected to each other, and that each GND is also electrically connected to each other. But we do need to add a power flag to here. Oh, and while we're here, let's set the reference and values for these capacitors that I forgot to assign earlier. Let's save and run the electrical rules check, which is this button up here. Okay, the first error, and this is why we run this, right? It's to catch these before we make the PCB. So, it says that the schematic is not fully annotated. Click Show Annotation dialog and click Annotate to auto-annotate any components that we forgot to do. Right, it was the power flags, and they've now been annotated. Let's rerun the ERC. Okay, this time 2 issues, one with VCC and one with J1, pin 2. Both these errors are shown with these red arrows. You can see that I didn't connect the VCC label correctly to the wire. Let's resolve that now. Right, now it's connected, save and rerun the ERC. Fantastic, no errors. Let's move on to assigning the footprints. To assign a footprint, select a component and press the E key on your keyboard. Come down to Footprint and then click this library symbol. Now we can search for a suitable footprint. I'm going to use surface mount capacitors, so with capacitor_SMD selected, in the filter I can search for the size I want. I have a bunch of 1206 sized capacitors in my component store, so I will select this, and I'm going to hand solder them, so I will select the hand solder footprint. If you've never soldered SMD components before, then I don't recommend using anything smaller than this. Even this size can be quite challenging. To see what it looks like, click this symbol and the 3D viewer will open. Double click to select. If you want to add a link to a datasheet for your component, enter the URL here. It's not necessary, but it will help you out in the future if you ever need to look anything up. Now it is just a case of repeating that for all of the capacitors. One tip here is that you can actually copy and paste this text in the footprint field. Let's save, and next I'll do the USB connector. I couldn't find a suitable pre-drawn footprint for the USB connector in my stock, so I drew my own footprint. A link to the footprint and the datasheet for the USB connector I'm using is in the description of the video, so you can use this if you want to. To import the footprint, click the Create, Delete and Edit Footprints button. Then select File, Import, Footprint. Navigate to the folder where you saved the downloaded footprint. Select it and click Open. So here is the footprint that I drew. I got the dimensions for this from the manufacturer's datasheet. If we view this in 3D, you'll notice that only the holes in the PCB are shown, as I've not drawn a 3D model for the USB connector. You can save in an existing library or create a new one. So File, New Library. Click OK. Choose where to save this. I'm going to save mine in the main KiCAD folder and call it My Library. So let's click Save and scroll down to My Library. Select it and click Save. Great, Now the imported footprint is in the library called My Library. So we can close the editor and assign the footprint to the USB connector. Scroll down to My Library and select the new USB footprint. Great, now let's do the fuse next. So search for fuse, and I'm going to use the same size for this fuse as I did for the surface mount capacitors. So here it is, 1206 hand solder. Alt 3 opens the 3D viewer, and this is what it will look like. Next, we need to do the resonator. Search crystal and then scroll down. I'm going to use a through-hole resonator for two reasons. One, I couldn't find any SMD versions in stock anywhere, and two, the SMD versions looked rather tricky to hand solder. So this footprint is the right one for the resonator I have. Let's take a quick peek at what it looks like in 3D. And this resonator is exactly the same physical size, so let's go ahead and do that one now. Next, let's do the UART chip. And as you can see, the variant of the chip I selected already has a footprint assigned to it, as well as the datasheet. Let's take a quick look. So here you can see that it's a surface mount chip, and this is what it will look like when it's on the board. Right, all of this section is now done. Let's do this diode next. Search for diode. I'll be using an SMD diode, and it will be the same size as the capacitors, so that's 1206, and select the hand solder variant. And a quick look in 3D. Next, let's set the pins for the ICSP header. Search CON. And it's a pin header with a spacing of 2.54mm. Now we look for the one that is 2x3. There are three versions, horizontal, vertical and SMD. Let's look at the difference. So this is the horizontal version, which is not the one I want. Then there's the vertical one, and this is the one that I'm going to use, but I'm not going to solder it in place. I'm just going to leave the holes in the circuit board. And of course there's the SMD version if you prefer. I want to use this one, so I'll select it now. Right, over on this side we have the LED, resistors and the chip to do. Let's take a look at the Atmega microcontroller. Here we can see that the default symbol already has a footprint and datasheet assigned to it. And this is what it looks like in 3D. Let's get the resistors done next. Search for res, and I'm going to use the SMD version and the same size as the capacitors, so again that's 1206. And again I want to use the hand solder variant of the footprint. Since I have a few more resistors, I'm going to copy this and then paste it into the other resistors. The LED is the last component we need to assign a footprint to. Search LED, and again I'm going to use an SMD version. This time the size I'll be using is slightly different to the other components. It's 1210. And of course I want the hand solder version. Right, now let's save our hard work. We now have all of the components drawn and a footprint assigned to each component. Before we move on, I'm going to perform one more ERC. Fantastic, no more errors. Be sure to hit that subscribe button and ring the bell so that you can join me in the next video where I'll walk you through laying out the PCB.